Okay, we are back. Okay, last time we stopped in this design principle of an operating system. We say a good operating system design is to keep mechanism and policies separate. It's like driving car and the car. They are two different things. Okay, and how to initiate or start an operating system. We call it booting an operating system. Usually it is rely on bootloader, which is a small program that run when a system was start up or power on. Okay, and the bootloader usually can be broken into several stages. Okay, a multi-stage bootloader may start with a simple bootloader that load a more sophisticated bootloader that then load the operating system. And this kind of cascaded boot sequence, sometimes we call it chain loading. Okay, there are two well-known chain loading mechanisms commonly used in the industry. First one is basic input-output system based booting. Sometimes we call it bias-based booting. Okay, another one is later and we call unified extensible firmware interface based booting. Okay, that's the more advanced booting sequence. Okay, and when loading the operating system, the bootloader, after loading the operating system, bootloader then transfer its control to the operating system. Operating system will initialize itself and load various modules when as needed. For example, a device driver and other file systems and so on. Okay. In general, the starting bootloader, the initial bootloader is reside in read-only memory. Okay. The basic operating system concept is following. Okay, an operating system contains some functionality, which are basically for all kinds of operations. They all have this functionality. Okay, it is a program, load and run other programs. That's the major objective or major functionality for the operating system. Okay, go through this, then they can load and run other user program. Okay, and also operating system provide an abstraction, so user application do not need to access the physical resource directly. Okay, but go through this operating system services. Okay? And to access these resources, usually include CPU, okay, memory, persistent files, and network. Also, other kind of devices. Okay, so these resources can only be accessed by through the service provided by the operating system. Okay, the user program cannot directly access these resources. Okay? So that's the basic functionality of an operating system. Okay? Provide the service to load and run a user program, and also provide services that let user program to access these hardware resources. Okay. In general, operating system itself are running in two different kind of modes. Okay, one is kernel mode, another one is user mode. Okay, the part which must be running in kernel mode, or sometimes we call it privileged or supervised or system mode, is that those instructions, they are privileged. Okay, so instructions, they are privileged and they can only be executed in kernel mode are those defined interrupt vectors. So you change or define the vector, the content of the interrupt vectors, and enable or disable interrupts. Okay, or sometimes interact with I/O ports. Okay, those instructions. others are set timers, okay, physical timer, and that's part of manipulate memory pages, okay. So set up the memory management units and so on. Okay. And other than this supervised or privileged instruction, okay, other part of the operating system, they are running in user mode because those part of operating system services, they don't need to execute this privileged instruction, so they can run in user mode. Okay, so modern CPU or modern processors, they usually support this two modes operations. Okay, they keep some privileged instruction, okay, in kernel mode. The other instruction can be run in by user mode. So user program usually running in user mode, and when they ask for the service of the operating system, depends on the instruction, the privilege needed by those operating system services. So operating system will change to kernel mode to execute those instructions, okay, for the user program, okay, and later they will transfer control back to the user mode and so on, okay. And this kind of mode switch, okay, usually provided for most of the processor. They use a special instruction, we call it trap instruction, or sometimes called software interrupt instruction, okay. And this special instruction can let processor the execution mode from user mode to switch to kernel mode, okay. And after this switch, then the previous instruction can be executed, okay. Some processor they may support explicit system call instructions instead of a trap instruction. And they can use they can have a lot of a set of system call instruction. So every system call they know how to execute or for trap type of mechanism, after you trap issue this trap system call or trapped instruction, not only the mode transfer to the kernel mode, and also the operation the CPU will go to a specific vector. Sometimes we call interrupt vector. So they go through this interrupt and fetch the starting address for that particular services. Okay, and then go to the corresponding service routine according to this address stored in interrupt vector table. Okay, so that's the trap instruction. Okay, doing, and for save this search in interrupt vector, and then go to corresponding starting address to set this. Some processor they offer explicit system call. So different type of service they use this system call instruction. Okay, so they go to the desired service directory instead of search the interrupt vector. Okay, so the system call or the mode switch may become much faster. Okay, so usually you have this two-way. One is use a single trap instruction, and then the actual address are stored in this interrupt vector table. Another way is every system call has its dedicated instruction. Okay, so the address stored inside this system call itself. So they go to the desired service directory. Okay, and both approach they can switch the processor to kernel mode. Okay. After switch to kernel mode, because now it's running in as operating system service. Okay, so the user programs, some context of the user program need to be set. For example, the program counter, okay, need to be set. So after the service finish, they can return to the right place. Okay, so first thing the system call or this trap service, they've set the current program counter on stack and transfer execution to a predefined address for the trap or from the system call itself. Okay, and control can switch back to the user mode and to the location after the trap by executing a return instruction from this interrupted instruction. Okay. So that's the basic mode switch mechanism. Okay, when a process try to access some system resource, they only provided by operation. So they issue this trap instruction. Okay. So most operating system they provide this system calls let user process interact with operating system. Okay, and usually a system call involve inside the system call they are implemented in such a way that they use a trap mechanism to switch control to operating system code, and those code are running in kernel mode. Okay, system code in general their flow as follows. First, set the system call number, okay, and set the parameters, issue the trap. Trap means you switch to kernel mode. When all operating system take control, they set the desired relative or relevant registers, and that's the requested work. Okay, do the actual operation for the user process. Then return from the exception, so back to the user mode, use the set relevant register to restore the context of the user process. Okay, and then after that, the system call can retrieve the result and return them to the calling function. Okay, so an operating system call usually implemented by these steps. Okay, so you can see the first the set system call number, set parameter, and last one retrieve result from and return to the calling function. These are executed in user mode. Only the trap instruction and inside this trap instruction, operating system take control, set relevant register, and do the actual operating system works. When return from the exception, okay, that's back to the user mode. Okay, those parts are executed in the kernel mode, and system call interface usually encapsulated or represented as library functions. So user process using these system libraries and to calling the operating service provided by the operating system. Okay. When an operating system decides that a process has been executed too long, it may preempt the process to run another process. Okay, so that's the preemptible scheduling. Okay, so in general, operating system can using a timer. Okay, so periodically it can be triggered to check that the current running process is used too much CPU already or not. Okay, and for example, this time interval usually are in 10 milliseconds or 20 milliseconds. Okay, so the timer will be triggered. So for example, every 10 milliseconds, operation can decide will be interrupted to change the running process and so on. Okay, by using this preemption mechanism, okay, so operating system can preempt the running process to get other process opportunity to use the CPU. Okay, and this kind of mechanism they force a context switch or killing the running process. Okay, killing running process usually means that if some abnormal happens, for example, running process keep running every time this process get access to CPU, it always use up its time interval or time quantum. Okay, for repeatedly. So maybe eventually the operating system will decide that this program has some misbehavior. Okay, so they will terminate the running process. Okay, in some special cases. Okay, to avoid a program running into something, for example, a finished loop or whatever. Okay, in general, in normal situation, operation only for doing the context switch. Okay, to suspend the running process and reassign CPU to execute other process. Okay. And also by using this time interval, only operation can decide either to preempt context switches other process, or for some hardware resources, operation can also use this time interval to check the status of the hardware. Okay, so decided to use hardware. Okay, depends on the status. Okay, to do some access, or maybe doing some bookkeeping for operation statistics. For example, okay, every time interval operation was take over and then record how much CPU time was used by the current running process. Okay, for example, if every 10 milliseconds interrupt, then this 10 milliseconds will counted into the statistics of the current running process. Okay, and so on. Okay, so this periodically involved or triggered, interrupted and operation gets control can let the operation decide to do some bookkeeping or holding the hardware status, or maybe do some context switching. Okay. So timer interrupt and context switching are tightly cooperated. Okay, every timer interrupt control transfer to an interrupt handler. Okay, in the kernel, and the processor switch to kernel mode. Okay, operation system then do something. Okay, for example, do these three things. Okay, depends on its current situation. Okay, and then after finish that operation, you can return. Okay, so it will issue a return from the interrupt process back to the running process. Okay. either back to the original process, or if it's time to switch to other process. Okay, then not only you need to set the context of the running process, okay, and restore the previously set context of another process. So it can select the process and restore its context and let that particular process to resume its operation. Okay, so the context, this we call it context switch. Okay, and the context usually include processors, relevant registers, okay, and program counters, stack pointers, and memory mapping informations. Okay, so set one process's context and restore the context of another one is we call it a context switch. Okay, so context switch contain two things: set context of current running process, restore the context of selected process. Okay, so the two things combined together is context switching. Okay, and this in general happen when a timer interrupt happen. Okay. Operator is also responsible to manage system devices. Okay. Usually there are three typical categories of devices. First one is character devices, mice, keyboard, audio player, scanner, and so on. Those are by-stream mechanical devices. So they accept, communicate by stream. Okay, so one byte at a time. Okay, and so on. Another type of devices we call it block devices. Okay, for example, disk drive and flash memory and so on. Those usually they communicate with the system. Okay, by not by at a time, but a block of bytes at a time. Okay, and usually these devices they can contain file system. Okay, they can store persistent data and so on. Okay, and because they are transferred, communicate with the system over the in block, not by the byte string. So block usually can be caged. The frequently used block may need to be caged in the system's memory. So they don't need to be retrieved from this device time to time. Okay? So in general, any device that can be used to hold a file system is a block device. And then the last one is network devices, is the name, or wireless networks. Okay, so Wi-Fi or GSM, okay, 4G or 5G, Stango, and so on. Okay, and those are they use packet-based interfaces. Okay, it's like a block device, but because it cannot be caged because that's from the network. Okay, a block followed by another block and so on. So and every packet, okay, in network we call it packet. Every packet is in general self-contained or self-addressable. So this packet contains some header information, specify the sender, receiver, and other error detection mechanisms. Okay, so when you receive or send out a packet, you should contain those information, and so to interact with a device. Okay, in general, most of the processor they use this device registers or command register associated with each device. Okay. And these registers usually are used to do some operations. For example, transmit transmit data, receive data, and set the status. For example, data ready, read, write, seek, and status, check it, and so on. Okay, so these are device registers that they can store some of these operation commands. So the operation system can communicate with this device by using this command register and set the operation. Okay, and another one, the device can be triggered or controlled by either memory mapped I/O. That means that these device drivers are mapped into memory address space. So standard memory instruction load and store can be used to interact with those devices. If the registers associated with the device are treated as in the spaces, then they can use those stored information to set the content of the register and to represent the operation the operation required for the device to operate. Okay. So some device, some processors or some operating system, they use this mechanism. Okay. Because the device usually they need to be set up to make sure it's ready to do some subsequent operations. Okay, and to check the device is ready. You have in general we have two ways. One is polling. Okay, so periodically the CPU check the status of the device from this device register. Okay, if it's become ready, then can send a request to the device to ask the device to do some subsequent operations. Okay, and this polling usually can be done when a time interrupt happens. Then the operation system can poll those associated devices simultaneously. Okay, so they don't need to waiting in the loop. Okay, and so on. Another way is by using interrupt from the device. Okay, so instead of operation system poll proactively to poll the status of the device, operation can just let the device to generally interrupt when it becomes ready. Okay, when device become ready to do something, then they can generate interrupt. So operation will be triggered to take over, and then you can take corresponding actions. Okay, so then there's no status check polling is needed. Okay, but because an interrupt may trigger actual context switch, so and the context switch is maybe costly. So depends on after the interrupt, the operation will generate actual context switch or not. Okay, if the interrupted device is happen to be the current running process. Okay, then there's no interrupt. No actual interrupt, no actual context switch will generate. Okay, But if the current running process just get access to CPU and then immediately be interrupted, then the previous context may become wasted, okay, and so on. So that depends on. So that's why we have these two mechanisms: polling, periodically polling usually is not preferred. Instead, the polling it may be done by associated with the time interrupt. Okay, so whenever timer was interrupt, operating system doing the context switch for the time content. Okay, and also check the status of those devices. Okay. That can be done, okay, in the same time. Okay. So that's a good polling mechanism. But interrupt is also to avoid actual context switch. Sometimes high priority process may set the interrupt disable mechanism. So when the first time the process get access to CPU, instead of immediately be interrupted by some device, they can set that. So for example, the next or set something disable the interrupt, so they can avoid being context switched, okay, during the first time interval, for example. Okay, there's a lot of different way to avoid this. Okay, to actually transfer data from device to memory or from memory to device. Okay, we have these two mechanisms. One is we call programmed I/O. Okay, that means the data can transfer between the device and the memory by CPU instructions. Okay, so CPU use read write to the device's memory directory. We can use the memory map device register, okay, to trigger the device and get the data to or from the device. Okay, and the processor, the CPU itself, is responsible to make the actual data movement. Okay, to read or write from the content of the register. Okay. Another way is the direct memory access, DMA mechanism. Okay, that means the device can send out or receive doing the transformation, data transfer to and from the system memory directory. Okay, the device can have the capability to access system memory bus. Use the memory directory, okay, without the processor to doing the actual instruction. Okay, so to use this DMA mechanism, the load device must be the device driver or device controller must be more sophisticated than this programmed I/O mechanism, okay, because and the system bus need to have a more sophisticated control. So when the CPU can execute its instruction without using the system bus. Okay, and when the system bus is free from the CPU, the device can use the system bus to do the data transfer. Okay, between the device and memory. Okay, so the system bus need to be controlled in such a way that the CPU and device did not conflict when accessing the bus. Okay, in general, CPU has a high priority. So when the CPU issue an instruction, they need to use system bus, then device will not get the access right. Okay, so when there's a when system bus become free, then the device will get control. Okay, and so the bus controller need to be able to resolve this access conflict between CPU and the device. Okay,